Hello friends, welcome to the last episode of my data science blog series. This is my 100th video. I'll be talking about a game. It starts with this arrangement of 16 honors cards, ace, king, queen, jack, clubs, diamond, hearts, spade, 4 into 4, 16 honors cards of a deck in a 4x4 array such that in any row or in any column there is no duplicate in suit and also no duplicate in denomination. This was done initially for the first time in 1726 by the French mathematician Jacques Ozanam. In late 1700, it went to Euler as the 36 officers problem. And then in 1959, Professor Rajchandra Bose and his student Professor Shikhande and Parker jointly disproved a conjecture by Euler that stood in the community for more than 150 years. So this is the story. I have devised a game out of it. So let me start with size 3. Cards are coming randomly here. There is no control on it. I need to place the cards in the cells in this 3x3 cells so that the final arrangement doesn't have any duplicate in any row or in any column in suit as well as in denomination. So let me put king of clubs here, king of dice here, queen of clubs, queen of dice here, queen of hearts, queen of clubs has only one place, ace of diamond has one place, ace of heart goes here, king of heart goes here, queen of hearts goes here, and ace of clubs goes here. That completes the 3x3 arrangement. It could be a solitary game or a couple game or a party game where these 9 cards are put on the table face down in a shuffled deck. Cards are in random order. One picks up one goes on picking up the cards and placing it in the 3x3 cell uh, such that in the final arrangement of 9 cards there is no duplicate in any row or in any column in suit as well as in dimension. So that is the game. It could be played as a solitary game, it could be a couple game where the persons take their turns, make their choices in turn, and then it could be a party game also where 3-4 players sit around and put the cards face down, put the 9 cards face down on the table, and one by one they place the card. The goal is to complete the arrangement. That's why I call it the completion game. Now 3x3 is easy, 4x4 is difficult. 4x4 is difficult. As per my calculation, if you try 2 billion times randomly, once or twice you will get the arrangement. So 4x4 is difficult. Let me play the 4x4. It starts the cards we have in this deck are coming in random are coming out randomly. You have no control on these cards and you have to place the cards in the cell completing the arrangement. No duplicate in any row or any column in suit as well as in dimension. And this could be a couple game, this could be a party game. So let me start with jack of spade. This is a hard arrangement, of course, no doubt. So ace king I put here, ace king ace, king ace, queen jack queen, jack queen, queen jack, queen jack queen, jack queen, ace king ace, ace king ace, ace king, queen jack diamond, ace king ace, only one place for King of Hearts, only one place for Queen of Spade, only one place for Queen of Clubs, Jack of Hearts, now Ace of Diamond, Queen of Diamond, Ace of Clubs, King of Clubs. That completes the 4x4 arrangement, and there is no duplicate in any row or in any column, either in the suit or in the denomination. Now there are several ways to come up with this arrangement. This is one way where the cards are given to you randomly and you have to just place them. Now why 4? Let us start with 1. We are putting double digit number. First digit stands for the suit, second digit stands for the denomination. So 1 by 1 is complete. 2 by 2, these are called Greco-Latin square. Euler first coined the term Latin squares and Greco-Latin squares. And 2 by 2 is impossible. I put 1 1 here, I put 1 0 here, and there is no place for 0 0. So 2 by 2 is impossible. 3 and 4 I did. Let me do a 5. 2 1 0 1 2 4 0. 4 0 will come here. 2 2. 2 3 will come here. 0 0 goes here. 3 4. 3 4 comes here. 4 2. 0 1 2. 4 2 comes here. 2 2. 1 1. 4 1 has one place. 0 4. 0 4 comes here. 3 1 has one place. 1 4. 0 1. 4 4. 0 3. 1 3. 3 0. 3 2. 2 0. 3 3. 1 0. 4 3. 1 2. 0 2. That completes the 5 by 5 arrangement, which is called 5 by 5 Greco-Latin square. And this is the, now you can see the algorithm. First digit forms the backward slashes, and the second digit forms the first digit forms the forward slashes, second digit forms the backward slashes. So that is the algorithm that we got, me and my sister Manjima, in 1996 when we were playing with Greco-Latin squares with colored paper. So this is the arrangement. This is the Molloy-Manjima algorithm for 5 by 5 Greco-Latin square, and this is true for any odd order Greco-Latin square. Any 3, 7, 9, everything could be done in this way. First digit, it should be same along the forward slash, and the second digit should be same on the backward slash. For even digits, for even orders, Molloy-Manjima algorithm fills up 50% of a cell, 50% of the cells for the even order Latin squares. And there is one method which is sequential method that works fine for odd order Greco-Latin squares, but for even it leaves only the last n cells blank. But for odd it works fine for both Molloy-Manjima algorithm and also the sequential algorithm. So let me display the sequential algorithm for order 6. We know order 6 Greco-Latin square is impossible, but I could put 34. I could cover 37 cells by trial and error. Only 2 left. That is the maximum. But using sequential method, one can do all the cells except the last 6. This is called the sequential method, and it works fine for odd order regulating square. For even order, it covers all the cells except the last n1. So 1, 2, 3, 4, 5, 6. Only 6 cells are left for 6 by 6 regulating square. And I don't know how to do 8 by 8 regulating square sequentially. There is another method that works for even order regulating square. Let me do it for 4 by 4. This is called lexicographic distance algorithm. So lexicography means put the cell with minimum I, and if there are multiple cells with minimum I values, take the one with minimum j value. So 0, 0 goes here. That covers the 4 by 4 cell. And I don't know how to do 8 by 8, but one gets patterns if one use lexicographic distances for 8. I don't know how to construct 8 by 8 regulating square with sequential order. This is 8 by 8, and 10 by 10 is a havoc work that's out of reach. I can't do a 10 by 10 regulating square except without computer search. But some people do it manually on pen and paper, but I don't know how to do that. Sorry, I made a mistake. I will use lexicographic distance. So I pick up this cell because it has the minimum I value among all the cells. This cell has minimum I value, but there are multiple cells, so I took the minimum j value. This is the lexicographic distance. It covers half the cells. 9 is possible with both sequential method and the Molloy-Mongeau algorithm, and 10 is out of reach. I'll stop here. I call this slide random versus sequential, where you can choose your method. You can have the cards randomly or sequentially, and you can try to complete the regulating squares. I stop here. Thank you. Like, comment, share, subscribe my video. I am available for one-to-one discussions too. I have my blog listing here in a text document where one clicks the name and the video starts. So if you want to have the blog listing, let me know. My email is daymolloy@gmail.com. Thank you.